So we'll turn to what is perhaps the most important example, the topology on R. At least other examples are similar on the real numbers. Now the open sets we would want are open intervals, A, B. However, the union of open intervals need not be an open interval. It could be many open intervals. So we'll use this to define open sets. We'll start with open intervals, but we'll also take their unions. So since this construction is going to be a little more general, I mean, for now we'll do it for real numbers. Let's look first at a set B, which is the set of all AB in R. Sorry, it's not a, it's a subset of R, so that A is less than B, and of course A and B are in real numbers. So we look at all open intervals inside the real numbers, and we'll let omega be omega B. Just to emphasize, this is contained in the power set, and omega will also be in the power set. It's the set of all unions of such things. So it's union of all alpha in A of S alpha, such that, well, of course, A is a set, so it's the index set, and S alpha is in B. B for basis, actually, where this construction will be more general. We look at collections of sets, which are open intervals, and we look at unions of collections of sets, but each of them has to be in B. Okay. And we'll show that this forms a topology. But before that, it's nicer to characterize being an element in omega B in a different way, which will make it more convenient. Otherwise, we could play around with unions and intersections, but this is a very useful way to think of it, and it will make our proofs a little cleaner. Okay. So suppose we take a subset of R in this case. Okay. But this will be in general or X appropriately. Then V is in this set omega B if and only if, I'll draw a picture in a moment, for all X in V there exists a set, let's call it J to emphasize it's an interval in B, such that X in J and J is yeah, that's it. Okay, so I was going to say J in R, but that is automatic. So J is a subset of B such that it contains these things. Okay, so we, as a general characterization, yes, the promised picture is that we have X and you think of B as being all intervals. So something is in a union of intervals. If given a point here, you can find an interval which contains X and which is contained in the union of all intervals. Sorry, not the union of all intervals, an appropriate union. Okay, so let's look at the proof of this proposition, which will allow the showing topology to be nice. And as I said, this will work in more general context also. In fact, all we are using is that omega B is union of sets of B, not that B are intervals or open in any way, just that B are contained in a fixed subset. Oh, I'm sorry, I should make a correction here. This is not 2 to the S, of course, but 2 to the R. More generally, it would be power set of X. Okay, so so first we have to show this in two directions. We have to show that if something is in, so suppose now first of all, V belongs to omega B. Okay, so that is V is going to be union alpha belongs to some index set A, S alpha with S alpha contained in the basis B. Okay, so suppose we have this situation, that is V is a union, and what do we have to show for all X? So let X belong to V. We have to show something about X. We have to show there exists J in B such that X belongs to J, but that's rather easy in this case. Okay, then as X belongs to the union alpha in A of S alpha, there exists alpha 0 such that X belongs to S alpha 0, but X alpha 0 is of course in B. Okay, so take J equals, J is just S alpha 0. So you can take J equals S alpha 0 to satisfy the condition. Now conversely, it looks a little like cheating the way we are doing things. Okay, conversely, suppose we have the following, that each point has a set in B that is contained. So we have, so suppose we are given V such that we have the right hand side. For all x in V, there exists some j, but I will call this specifically jx in B, such that x is in J. And again specifically jx. Okay, then what we'll do is the following. So each point has some interval around it, or set in B. So we'll make the following claim, that V is actually the union of a collection of sets in S alpha. Namely, I'll take all jx, where x is in the set V itself. Note, this is a really big collection. It need not be countable. We will see with the real line we can reduce to countable collections post facto, but this is a useful trick, and you can't always reduce the size of the collection. So V is x in V, this thing. Okay, so then we can take A is V given the claim. So we take A is V, and we take J alpha is just going to be, sorry, S alpha is J alpha. For alpha is going to be in the index set, alpha belongs to A, which is V. Okay, so this is all this is given the claim. Okay, so of course the way we prove claim is we prove inclusion on both sides. Namely, if x belongs to V, okay, then what do we know? We know that then x belongs to Jx. So which is contained in union x belongs to V of Jx. Okay, so let me call this x0 because we are using this. X0 belongs to Jx0, which is of course contained in union of Jx. Okay, so thus V is contained in the union x belongs to V of Jx. And the converse is also simple. Okay, so if x, now again let me call it x0, belongs to we need not do it by looking at elements, we'll use properties of unions. So conversely, what is the converse we want to show? This union is contained in V. Conversely, Jx is contained in V for all x. Okay, hence union x belongs to x, V of Jx is contained in V. Because if each individual set is contained in V, then the union is contained in V. Okay, so one last time before we move on to the specific case of real numbers, this is a completely general statement about the union of sets. It says that if we have a given collection of sets B and we are looking at all unions of collections in B, then something is in that if and only if given some set V is such a union, if and only if any point in V is contained in a set of that nature. Okay, so with this in hand, we can show that we actually have a topology on real numbers. That is, it behaves well with respect to unions, finite intersections, and the third property, which is simple. So let's look at what we needed. We wanted the axioms for the topology on R. The first one is that it's closed under union. Okay, so suppose if V belongs to omega, which you remember is this omega of B, that is, it's a union of open intervals, and if V alpha belongs to omega for all alpha in A, okay, then we have to show the following claim. So this is the claim here. Then union alpha in A of V alpha belongs to omega. Now this argument is completely general. It needs no properties at all of B. Okay, so namely, let me prove the claim. So the proof of the claim is if x. So what do we have to show? So if x belongs to union of alpha belongs to A, V alpha, then x belongs to V alpha and V alpha belongs to B for some alpha in A. That is, what we just showed is what we wanted. For all x in this union of alpha in A V alpha, there exists some set which we last time called J. In this case, J is V alpha, such that there exists J which is in B, such that x belongs to J. Okay. So this completes the claim of proof of this claim, that if x is in the union, if the union of these sets, so by the above characterization, so thus union alpha belongs to A of V alpha is in the set omega. Okay. So this needed nothing. Again, I emphasize because we will see this argument again where B is replaced by something else. But the intersection needs something. Okay, so we have to somewhere use the fact that we have an interval. And let's try to narrow down exactly what we need there. Okay, so suppose V1, Vn belong to omega B, omega which is omega B. Okay. And now we will actually use the details of what B is, but we'll still use this characterization. Okay, so it means that for each Vi and a given a point, there's an open interval which is contained in that Vi if we have a point in Vi. Okay, so we show, so this is the claim here. And what do we claim here? Then V1 intersection Vn, n-fold intersection, is also an open set. It belongs to the topology. Okay, so proof, well, again we have to take a point x belongs to V1 intersection Vn, and we show that there is that appropriate set J for this. Okay, so then x belongs to Vi for all I. Hence there exists a Ji, okay, which is contained Ji such that x belongs to Ji and Ji is contained in V. So that is the characterization of being a union of sets. You can find some Ji. Of course the point is this Ji is in B. Okay, so let Ji is an open interval. So this is Ai and Bi. Okay, so then what we know is that Ai is less than x is less than Bi. And finally we see some actual picture. So here is x, here's the real line which missed my x, so let's put the x on the real line. And then I have my intervals. So there is Ai and there's Bi before and after this. So then you might have, so now the AIs can be nested in different ways. You may have a smaller interval, or your purple interval may be smaller on one side and bigger on the other side, etc. But they're all intervals which begin before x and end after x. So it's quite clear how to get an interval from these. Okay, namely, we take the maximum and the minimum of these things. So you let A is maximum of A1 to An, and B is minimum of B1 Bn. Okay, so since these are finitely many, we can take the maximum and minimum. Note this doesn't work for arbitrary intersections. Okay, so let A is maximum of these, B is minimum of these things. So then what we know is that AB is contained in AIBI, and AIBI is contained in V I for all I. So this implies that AB is contained in the intersection V1 Vn, and of course AB is an open interval. It contains in basis. Okay, and x belongs to AB because A is less than x and B is greater than x. Okay, so you take J equals the interval AB. So that to satisfy the claim that any point is contained in an interval which is contained in the intersection, hence the intersection is a union of open intervals. Okay, so one could have used distributivity of open sets and over closed sets, and I mean unions and intersections over each other, and proved this as well, but that would be more messy. Nevertheless, this is a very useful way of thinking of it. So set is a union of intervals provided given any point in the set there's an interval that's contained entirely in the set, and x is a point in that, and conversely. So this disposes of the main property, and this proves the main property. Now we just have to dispose of the property 3, which is rather simple. So we can just do so on the next page. So of course 3 phi is the empty union. So we have an empty collection, that means the index set is the empty set, and we have a set associated to every term in the index set. There are none at all, so there is only one empty union. And how about omega? So omega is, there are many ways to write it, but for example I can take n as being positive integers and take the union of minus n. So sorry, not omega, of course, the whole space X, which in this case is R, is these. So hence, or thus phi and R also belong to omega. Okay, so this establishes a very important example. When we define continuity, you will see that this example coincides with the topology in this example coincides with the usual notion of continuity on real lines in terms of epsilon delta. This indeed generalizes in many ways. We have implicitly also seen a next concept for the next lecture, which is that of basis of a topological space.